The goal of this video is that at the end of it, you'll be able to make your own simple PCB and get it manufactured using EasyEDA, which is a tool that JLCPCB has made to make it much easier to create your own PCBs. And I picked EasyEDA because it's just so simple. It solves a lot of really tricky problems that are harder to solve with some of the commercial products that are out there or with KiCad. I am assuming a certain level of electronics experience already. If you don't know what a capacitor, a resistor, a transistor are, what power supplies are, and the basics of like digital logic signaling and so forth, this is going to be really hard for you. It's going to be hard to learn those things as you're making a PCB. My background is in physics. I was trained as a physicist and dropped out in grad school and went into computer programming. I've spent a long career doing computer programming, and I've always been hardware curious. I love making devices that interact in the real world with programming and custom hardware and so forth. Matter of fact, I have a little something that I made right here. This is a failed attempt at a meditation timer. It's got a Raspberry Pi Pico inside of it, and I really want to rebuild this and make it a better product with a custom PCB, and I'll be getting around to that one of these days. But I could make it much smaller and much more reliable if I just made a custom PCB with all of the features that I want on it versus packing in multiple non-custom PCBs that resulted in this huge device here. We need the right project for our first PCB, so I decided to start out with something relatively simple. I started working with ChatGPT, and this is something I'm going to instill in the very beginning. Generative AI is your friend. If you're starting out in a subject matter that you really don't understand very well, there's no way you're going to have a PhD engineer on call to help answer all the questions that you have. But with generative AI, you do. You have a PhD electrical engineer in your pocket. It's going to be wrong sometimes, but it's going to be way better than nothing. ChatGPT has been a wonderful help to me in terms of just kind of bouncing ideas off of it. It knows a ton about electrical engineering. It knows a ton about building PCBs. Whenever you run into a sticky question or you don't quite know how to do things, you can always ask ChatGPT and it'll help you out. So I want to show you kind of how I started out on this project. So I decided that what I wanted to do was create a simple USB breakout board. So a USB breakout board will provide the 5 volts that USB provides to a DIY project, so maybe a breadboard project, perhaps provide some other voltages, maybe like 3.3 voltage, and also provide a serial interface. So if you want to talk to your microcontroller or other projects using a serial interface. I picked this project because it has a relatively low component count and it's relatively easy to do on a 2-layer PCB. And we'll talk about what 2-layer means in a bit, but it's just a simpler and cheaper way of doing a PCB, and it's ideal for your first project. So we've got a relatively low component count, a relatively simple PCB, and a final product that is both simple and usable. It's something that you will actually be able to use. It's got almost all of the basic components that you will need to know in a more complex board. So even though there is no microcontroller in this design, there are some of the more complex things that you need to know when you're stepping up to powering and utilizing a microcontroller. So let's start out with a conversation that I had with ChatGPT. And I made sure to log on as a free user, so I'm not getting anything more advanced than what you might be able to get from ChatGPT. So I started out with my general goal. So I told it I'd like to design a simple USB breakout board as a first PCB project, maybe with a UART so that I can use the board to talk to microcontrollers. And it says, great. Now, obviously, ChatGPT is nothing but if affirming, and so it tells me this is a great idea. But then it also starts to talk about, some of the design decisions that we might have. How do I want to connect to it? What sort of USB connector do I want? Do I want USB or micro USB? It gives me some of the options for a UART bridge chip So there are quite a few different options here, and we talk through some of those. How might I want to power it? And then what sorts of pins do I want to pass out from the UART interface? The UART has a transmit and receive, so that basically the UART is just a serial interface that you can use to talk to typically older things, but almost everything supports some form of wireline serial interface. Almost every microcontroller does, at least. So you could just plug this. If you have a breadboard project with a microcontroller in it, you can plug the transmit and receive pins into this and just talk to it over your USB port. But there's also some optional things where we could pass through some of the other serial interface control logic as well, and we might do that. And it talks about, what sort of a header I might use, and it gives me a little schematic sketch. And already it's talking about some of the things that we need to think about here that you might not know if you never designed a PCB with a USB interface. It says we need some electrostatic discharge protection and also a polyfuse. I don't know quite what a polyfuse is, but we can ask ChatGPT what that is later. It has some tips for laying out our PCB, talks about decoupling capacitors. We can talk about that in a little bit. And then it says it can draft a complete schematic. One thing I would coach you not to do is don't have ChatGPT draw anything for you. It's terrible at drawing. It will draw circuits that are wrong and bad. I've had it try and produce schematics. It's horrible. It's awful. Don't ever do it. What it's really good is describing things in words. So if you have any question about how things should connect to each other, ask it to describe what should connect to what. And it does actually a really good job of it. And then I make a little bit of a mistake here. I say I'd like this all to be hand solderable. And we go down a little bit of a rabbit hole of how to make it all hand solderable, but we run into kind of a little bit of a big issue. I want this to be USB-C, just for future compatibility's sake. When you go and you look at Amazon, there's a whole bunch of these little boards, and they all are like USB-A. And there's one reason, is because they are hand solderable. USB-C connectors, however, are not hand solderable. They have little tiny pins with a very small pitch, and it's difficult to hand solder them. Because I'm really attached to using USB-C on this, I eventually threw away the idea of making it hand solderable. This frees up some other design decisions that make this board easier to design as well. Now, the difference between a hand solderable board and a board that's not hand solderable is typically in the components that you choose. If you want it to be hand solderable, you would choose larger components. And we'll talk about component sizings in a little bit. You would typically choose 08, 05 or larger for surface mount components, and you would prefer chips that have a relatively large pin spacing and maybe even a through-hole chip as well. Those are much easier to solder onto your board. Because we're doing away with that, we're actually going to use some components that are smaller, that have pins that are very close to one another, and you will have to get this board assembled. Unless you have very advanced soldering skills, and I do not, you will have to get this board assembled by the manufacturer, which is really not that big of a deal. Most places like PCBWay and JLCPCB have very affordable assembly. And I will actually link to this discussion so I can share this discussion out to folks so that you can see the thought process that went into this and my interaction. And as I go on, I'm going to be adding to this, so you'll be able to see this entire conversation that I had with ChatGPT as I progress with this design. So here we had decided on the USB-C connector, so we got rid of that idea of hand solderability, and now we're down to what should be our USB to UART bridge chip. And it gives me a number of different options. And then we talk about what we can break out. At the minimum, what we want to do is we want to break out the transmit and the receive, the ground, and then the VCC or the 5 volts that it's coming from the USB connector. Okay, and then we talk about a polyfuse, and I did ask ChatGPT what a polyfuse is, and it told me that it is basically a resettable fuse. So what you want a polyfuse for is if anything on your board were to short out, so maybe you soldered something wrong, or maybe you designed something wrong and you plug it in and there's a short on your board, the polyfuse will disconnect the USB connection. If you don't have that, you could short out the USB connection and then it could travel up to whatever your USB cable is connected to. So if it's connected to your laptop, it could short out your laptop, so it could damage your laptop. So the polyfuse is just a little bit of resettable protection. ESD diode array. So what those do is they are voltage clamps that make sure that if there's any sort of a static discharge on the USB lines, so somebody comes along and they're rubbing their feet on the carpet and they touch your USB cable and there's a, I don't know, there could be like a 5,000 volt shock that travels over those USB lines. What the ESD diode array does is it shorts that to ground, so it won't affect your componentry. And it basically, what it does is it protects the chips that are on your PCB. And then we talk about decoupling caps on every power pin. I'll talk about what that is in a little bit. And then it's giving me some advice. So it says route D plus and D minus as differential pairs, matched link, 90 ohm differential impedance. So it says KiCad has tools for this. We're going to be using EasyEDA Pro, which is the house design tool for JLCPCB. And it also has some differential pair routing. Almost all of that probably just sounds like Greek to you. It did to me many, many months ago, but it all kind of makes sense. It's not terribly important for lower speed USB. It just isn't all that important, but we'll go through it because it can be important for higher speed interfaces. Like if you're doing differential signaling for a, say like a video or a Ethernet or something like that. If you ever get around to doing something more high speed in the future, differential pairs are important. So here I'm zeroing in on one of the chips that it recommended. I want it to tell me more about the CP2102N. It gives me a little bit of an overview, tells me why it's good, all the things that it can do, some of the limitations, and one of the things that it says is that the package is QFN, which is a smaller package, and it has a small pitch. So that means that the pads on it are very, very small, 1/2 millimeter. It's not really hand solderable, but if you're having it assembled by the manufacturing house, it's not really a big deal. Then it mentioned that the CP2102 has some GPIO pins, and I think it said something about it being able to drive a transmit and receive LED light, which would be a cool feature to have on our PCB. We want to know if it's talking and in what direction it's talking. So can we use those GPIO pins that it said that it has to trigger those LEDs? And it tells me how it works. It has up to 7 GPIO pins, and I think a couple of them can be configured to toggle when it's transmitting or receiving. Then it talks me through LED wiring, and then we talk about programming this part. It actually is relatively intelligent, and it's programmable through its own USB port. And we're not really going to program it much, but we can configure it to have a different USB ID. So when you plug it in, it could say, like Josh's USB to serial port adapter. And then we can also configure it to say what those GPIO ports are going to do. So until we configure it, the LED status lights won't work, but once we configure it, it'll turn that functionality on. And then we also talk about powering this. This particular chip, the CP2102, has a number of different options. You can power it with 5 volts, you can power it with 3 volts, and it also has its own internal regulator. So you could power it with 5 volts and it steps it down to 3 volts. So I thought, well, hey, maybe that's kind of cool. Maybe I could use that 3 volts that it puts out to break out a 3.3 volt option on our breakout header. But it turns out that it only supports about 1/10 of an amp or 100 milliamps. So that wouldn't provide a lot of power for whatever thing you wanted to power with 3.3 volts from your USB port. We talked about it a little bit and decided that I was going to have an external regulator. So what we'll do is we'll put an LDO in there, and LDO stands for low dropout regulator. It's a voltage regulator that will take 5 volts from the USB-C connection and step it down to 3.3 volts. And it will typically handle about 1/2 amp or 500 milliamps. That's more than enough to power both the CP2102 and your own projects. So cool, win-win. It just adds a little bit of complexity to the product. So again, here you can kind of see the diagramming ability of ChatGPT. It's not great. I'm not exactly sure what it's doing, but it gives you a general idea. Again, I think it's much better when it just talks through how things should be. And then I tell it that I found a 20-pin part on LCSC. LCSC is the parts provider for JLCPCB. So we talk about this particular chip and its packaging, and then it has a text description schematic here where it talks through basically everything that we would want to have in this design. And based on my experience, this is pretty comprehensive. I don't think it's missed a lot here, and I don't think it's really missed anything. And then it talks through the header that we're going to have. So this board will take USB and break it out to header pins that you can attach little terminals on. It's saying that we should take the 5 volts from the USB, we should take 3.3 volts from our LDO, ground, transmit, receive, and then also RSTB. I don't think I want to do that. I think I just want the RTS and the CTS signals. I think basically in what I've read, that's a good level of things to break out. And also, just perusing on Amazon, you can see a number of these different options here. So you can see actually what I'm talking about. Some of them are kind of embedded here, where it just has a breakout pin, color-coded breakout pins. And here we have one that's relatively nice. It's got little selectors for the voltage, and then it's got pinouts here. Stuff like this. This is close to what we'll be making, something like this, perhaps with a couple more pins out. This might even be the same chip, I'm not sure. But this can be pretty close to what we actually end up making. Yes, it is. So that is the CP2102. So this is actually going to be relatively close. But you can see one of the big differences is that this has a USB-A connector. We're going to be using USB-C. So now I'm going to ask it to summarize, and I'm going to ask it to give me a final schematic description and a total bill of materials, or a BOM. And so this is really pretty cool. It talks about the USB-C connections, the power and regulation connections, and how everything should connect. We talk about the CP2102 and how it should connect, the status LEDs, ESD protection, and then the header pinouts. And then it has a final full bill of materials here and the package, which is really, this is kind of amazing. Like, if you didn't know anything about making a PCB, I mean, I haven't asked it particularly involved questions. I could have come to it with, being a total novice, and it would have given me this. Now, you have to have some level of experience to understand what all this is, but I understand all this because I've talked through it with ChatGPT. It's really good at when, I go, well, what's a polyfuse? What is QFN? What's that stand for? What's ESD? So forth and so on. Every step of the way, if there's something you do not understand, you can ask ChatGPT to explain it. I mean, I think this has done a really good job of giving us just a basic approach to how we're going to do this particular project. So let's get started. Let's get into it. We're going to go to EasyEDA Pro. You go here and you have to click this little load, and then you go to Pro Edition, and I am logged in here. So what we're going to do is we're going to create a new project here. So we go File, New Project, and we give it a name. So we're going to call it UART Breakout Board for USB-C. And it goes ahead and creates this project. And we have 2 items here. We have a schematic and a PCB. And this is one of the things that I kind of needed to learn when I first started out. The schematic is a conceptual layout of your circuit. So it says it's basically a wireframe of your circuit. It's not related to physical reality. It's just saying that X is connected to Y is connected to D. That's it. There is nothing about the real world wires that are underneath this. There's nothing about the actual implementation of that circuit on a PCB in the schematic. It's meant to just present a quote unquote schematic outline of your circuit. It should be easy to read. The PCB is the real-world implementation of that schematic. So how am I going to connect port A to port B. It's going to be a wire, and the wire has to be of a certain thickness, and it has to go along this particular route. And oh, it can't go in that route because there's another one that crosses it. So how do I handle those sorts of things? So the PCB has all the messiness of the physical constraints of the real world, whereas the schematic is just talking conceptually high level. How are these things connected together? We always start with the schematic, and then we update the PCB from the schematic. I think you can go the opposite direction, but I never go that way. I always make changes on my schematic in terms of what parts are there and the connections that go to each other, and then update the PCB from it. So the way we start this out is we go to place a component on here, and we're going to go back to our list of our bill of materials, and one of the top things that we need is this CPO2, QFN, so forth and so on. So we're going to go back into our schematic. We're going to do place and device or reuse block and search for that particular component. Now, when I type that particular part number in here, the exact part number, it found exactly one thing, but one of the problems that we see here is that it says LSC stock and the JLCP stock is 0. And we don't want that. Also, this is a much more expensive part than I think it's supposed to be, so I'm going to widen the search here a little bit. And there we go. I think we found it here. So we see this one that has several thousand in stock, so 7,000 in stock. So this is CP2102N. It's just a slightly different part number. So, you know, ChatGPT can't know everything, but that's something to keep track of. Whenever you search for a part number here, you can search by a manufacturing part, you can search by the types of parts and so forth, but you need to pay attention to whether or not LC, SC, and JLCPCB have it in stock. Because if it's not in stock, when you go to order your PCB, it's going to say, hey, I don't have this part, I can't make it for you. One of the things I want to kind of bang into your head is that whenever you use a complicated part that you're not familiar with, you should click through and go look at the data sheet. So this is the Silicon Labs data sheet for this chip. And it's got a lot of great information about, you know, how this chip functions. Remember when I was asking about whether or not I wanted to power this with 5 volts or 3 volts, it talks through the right ways to do that and how you're supposed to configure all the various pins on this device for various different ways of powering it. But it also talks about having ESD protection, and it recommends a part here. So maybe we could use that part recommendation for our ESD protection. Then it talks about all the various GPIOs that are available on this chip. And so this is a generic data sheet, and you'll find this a lot if there are different packages for a particular chip. It's very frequent that they'll have simpler packaging that'll have fewer pins and expose less functionality, and more complicated packaging that has more pins and exposes more of the functionality. Here's the 28-pin version of this. We chose the 20-pin version of it for simplicity because we don't need all those features. So if we scroll down, we see the 24-pin version, and then if we keep going, we'll see the version that we picked. So this is the actual pinout of our chip. And so there is pin 1, and oftentimes pin 1 will be denoted with a dot in the PCB and actually physically on the chip. And sometimes they'll actually silk screen a dot onto the PCB so that you can always be sure that things are aligned properly, because you can rotate this chip and it could be soldered on in 4 different positions, and 3 of them would be wrong. So it's important that the dot denote pin 1 and that everything be aligned around that so that you can clearly see whether or not your chip is oriented properly. But then it talks through all of the functionality of each one of these pins in detail. So I would suggest that if you have a part that you're not familiar with, you read the datasheet back to front so that you really, really understand the packaging and any other notes. So lots of times they'll give you sample schematics for wiring it up, and sometimes they'll even give you sample PCB layouts if the PCB layout is particularly critical. So anyway, we've found the right chip. We click place over here, and that places it on here. Now we're going to go for the USB-C connector. And actually, one of the things I'm going to do is I'm going to show you how to search this a little bit more differently. What you can do is you can filter to connectors here, And we're going to go for, we can scroll down and look at the types of connectors. So this is a cool way of searching. We should be able to find USB-C. Yeah, okay, sorry. That's weird. Okay, so USB connectors. Here we can see at the top of the list are some Type-C 16-pin connectors that have just ridiculous stock counts. So these mean these are incredibly common. They have a huge number of them in stock and everybody's using them. So I don't think you could really go wrong with any of these. So we're going to go ahead and use this Type-C 16-pin 2MD. I think I've used this one before because it just pops up to the top of the list all the time when you search for it. But one of the things you can do if you get used to a particular part, you can copy the LCSC part number here. So you can copy that off. You can save it somewhere in a document or a spreadsheet. And when you want to find it again, you can just go to the search, paste your LCSC part number in here and find it again. You know, it's just, it found the page that I'm on. But we can search up here and do the search and see we find it again. And then we're going to go ahead and place it. So we see our USB-C connector there and all of its pins, and you get an idea that it is relatively complicated beastie. One of the cool things you can do is you hit the space bar to rotate things, so if you want things in a different orientation. So there we go. There's two relatively major components, and now we have the LDO regulator. So it's recommending a 3.3 volt LDO regulator. So we can go into the EasyEDA tab over here and search for LDOs and power management, voltage regulators. And this is a key thing, and this is the first place where we're going to be able to pick a basic part versus an extended part. When you're using JLCPCB to assemble your project for you, they have economic assembly and just standard assembly. For economic assembly, you are charged a $3 fee for every part number that you have that is not a basic part. So if you use a basic part, what it's basically, the reason that they do this is that they have machines that are loaded up with all of their basic parts. They have tons of basic parts, and they can just run your board through those machines. Those machines are running 24/7. They keep them constantly loaded with the right parts, and they're always in the same space. Extended parts are less frequently used. They're ad hoc and so forth, and so they might only be used for one board every other day, something like that. So they actually have to physically go out and load a reel of components into a machine to be able to make your board, and that costs them money. So that's why if they're trying to do economic assembly, they would prefer that you use the basic parts that are pre-configured and easier and cheaper for them to use. So if you select a basic part, you're going to get cheaper assembly. So I would recommend, if you can, using this EasyEDA tab in the part picker, and you can do apply and a filter. And what you immediately see is there aren't a ton of basic parts here, but one of the ones that you can see is the AMS 1117 3.3 volts. And the old hands in any of the PCB forums on Reddits will absolutely be screaming at me when I tell you to pick this part. Oops, I just placed it twice. It's a relatively out-of-date LDO regulator. It's probably not terribly efficient, but it works, and it's a basic part, and we're going to use it, and it's going to be fine. And we want a resettable poly fuse. And it's recommending a part number here. So let's see if that part number is at all usable and if JLCPCB has it. So search LCSC electronics. So we found the poly fuse here. If we have any question about this, we would obviously want to check out the datasheet and see, what it actually is. Let's go ahead and place this item in our project. So now it's recommending this TVS diode, and it's a TVS diode and a ESD array. So for ESD protection, I did a little bit of research with ChatGPT and online, and I found a part number that I think is good. And so we're going to place this, and we're going to do 2 of them. We use that to provide a path to ground for any static electricity or any spurious signals that go over the USB lines. Come back up here. So we have the poly fuse, we got our ESD, And then we want 5.1K CC pull downs. Okay, so we're going to go here and place device. And here we're going to do EasyEDA, clear out our thing, and we're going to go to resistors. And this is where it can get confusing. There's a lot of different resistors in here, right? And it's not immediately obvious to you which ones to pick. And, you know, metal oxide, metal alloy resistors, like, you know, if you know what you need, you know, if you know, you know, but when you come in here the first time, you don't know. And I wish there was a way to just say, give me like the normal surface mount capacitors. And you just have to know what those are. And the normal surface mount capacitors are the just chip resistor surface mount. Okay, but we've loaded this up and it's giving us a huge amount of parts. So again, we want to select the basic part filter, apply our filters, and then do 5.1K and select 5.1K and apply filters. There we go. So we got two parts here that have really high stock numbers. So really the big difference between them is size. So this is a 0402, this is a 0805, and this is an 0603. So we get three different sizes. Now is the time to introduce a little tutorial on surface mount footprints. So I found this website that talks through the various packages, and it goes just far beyond the little resistor package that we're talking about. So I'll link this in the description here, but this is the basic resistance capacitor inductor sizing chart. You can see the very tiniest. I don't think I've ever seen that. 0201, which is extremely tiny. I think it's about the smallest that you would see commonly used. 0402 is a quite common package size. It's probably the smallest that you would usually see on most boards. 0603 is a very, very common kind of intermediate size, although when you look at one on a board, they're still incredibly tiny. 0805 is getting into the territory where you can touch it with your hand and conceivably hand solder it. So originally when I was going to go for a hand solderable board, I thought, well, why don't we use 0805? But I kind of gave up on that, so it's not terribly important to me that we use 0805. So we'll pick whatever is just the most convenient. And then you have 1206 and onward and upward, and you can see the various sizes. And then we scroll down, we'll see some of the other packages here. So these are kind of older packages with 6 leads, so TSOP 06. So lots of times you'll see these codes and you don't really know what they are. They're just kind of standards for packages that specify how big the package is, where the leads are, how many leads there are, and so forth. MOSFETs, transistor packages. So this is not at all, you know, oh, we do have some other ones, ZIP, DIF, PGA, QFN, LGA, various DIP dimensions and so forth. And then, oh, God, this is great. So anyway, back to picking our resistor. I think I'm just going to go for the middle ground 0603. And remember it said that we needed 2 of them. And they need to go near this USB connector. And now we come to the capacitors. So what the capacitors are used for is decoupling. What they do is they filter out noise, so high frequency switching noise. These are complicated devices. They have internal clocks. They have transistors which are switching, pulling current, not pulling current. I mean, they're just noisy as all heck. What a capacitor does is it provides a buffer, and they can also provide like an extra little battery. So if the chip has a spike in current draw, instead of like pulling down a 5-volt rail, it will draw from that capacitor for a very short period of time to provide the extra power that that chip needs. So it's important for reliable functioning of a circuit. So it's recommending a 10 microfarad decoupling cap for C in and C out on the LDO regulator. So I'm going to go ahead and find let's go ahead and save this while we're at it. Place. And we're going to go over here and select capacitor. And again, with capacitors, there's a whole bunch of options, and you're like, well, just tell me what you would normally use. And there is a kind that you normally use. It's just called multi-layer ceramic capacitor. For anything that you would normally do, just a standard decoupling capacitor, the multi-layer ceramic capacitor is probably just fine. I don't know that I've used anything else yet in my designs. That probably says I'm still a beginner, but whatever. So we're going to select the basic part here again, apply the filters, and then we're going to go 10, what was it, 10 microfarad? Yes, 10 microfarad. So 10, and I don't think I can type the U, so I just have to find it here. And we're just going to go for 0603 because it's a little bit smaller, so it'll make routing a little bit easier. So do that one, and we're going to place 2 of them. And then go back here. So that's for C in and C out, so it wants us to put it across the 5-volt rail and the 3-volt rail. So the LDO takes 5-volt input from the USB, and we're going to put a capacitor between that 5-volt input and ground, and then it produces 3.3 volts output, so we're going to put a capacitor between that 3.3 volts output and ground. And we're going to have 2 decoupling caps for the CP2102. So it wants 1 microfarad and 1/10 of a microfarad, so 100 nanofarads. Okay, my filters, now we gotta get rid of that and do 1 microfarad. Okay, so we have a Samsung 0603 that has a high stock number. Let's just go ahead with that for our 1 microfarad. And then we want 100 nanofarads. We found the 0603 part, and this is we'll put these over there, actually. Let's put them near where they need to go. Go back here, decoupling caps, and we have 2 different decoupling caps because different size capacitors handle different frequencies well. So they filter out the various frequencies. One is a bulk, so it might handle, large current draws, and another one is designed to filter out the noise, like all the switching noise from the interior of the chip, or stuff that might be coming over the voltage rail from other places. Well, it filters that out. Then we need 2 indicator LEDs. I've got a part number for an LED that I found before, that I've used before. So this is a basic part. It's in stock, and it's a red LED. So, and it's 0805, which is a little bit bigger, so maybe that'll be actually a little bit more visible. So let's go ahead and place 2 of those. A reset tactile switch. I don't think we're going to do that. And then it wants a 1x8 header. I don't think we're going to have enough room for a 1x8 header. So what we're going to do is we're going to put 2. So let's do 1, 4P, and through hole, and then do apply. There we go. So that's a beautiful little thing. And it's relatively cheap. It's like 2 cents. Let's go ahead and place that on our schematic. I think this is relatively close to our final bill of materials. We don't have much more to add here. We might have to sort through a couple other things, but I think we can go ahead and wire this up. Okay, so now we have adjusted the schematic a little bit. We added a push button, so the chip exposes a reset button that if you push it to ground will reset the UART, which might be a handy capability to have. And then we're also going to break out, because we have 1 extra pin, we're going to break that out, which would allow something externally to reset the chip. So you might be able to use this to hold the UART, turn the UART off until a microcontroller is ready to talk to it. So that could be a handy feature to have on your breakout. We've got all the components that we need here, and now what we need to do is wire them up. And I've talked with ChatGPT a little bit and asked it basically, what do I need to do with all the pins that are on here? And let's scroll back down here. So I gave it a screenshot of the pinout from the datasheet. So you could read through the datasheet as well and look at all those things and so forth. And I did read through the data sheet, but we can also ask ChatGPT, like, what's your opinion of what we should do with all these, and see if it makes sense. And so it recommends what we should do with every single pin. And this is really, really important. You should have a positive idea of what to do with every single pin on every single integrated circuit on your board, like without exception. Like, you should never just go, I don't know what that pin does. They will usually tell you in the data sheet what to do if you don't use it. So typically you might need to tie it to ground, you might need to tie it to 5 volts or 3 volts, or you might need to tie it to ground with a resistor or so forth, or maybe tie it to another pin. Or they will tell you if you can leave it floating, or what's called not connected. But there are some cases where if you leave a pin on a chip floating, even if you're not using it, you could basically destroy the circuit entirely. It just wouldn't work. So you need to know exactly what to do with these. And I've read through this, and this all makes sense to me. And I will double check it with the data sheet as well, just to make sure that we're not hallucinating anything here. Great, so now what we need to do is we need to start wiring this up. So we're gonna start with the USB shell here, and we're just gonna zoom in a little bit. And I'm not gonna have a huge tutorial on the mechanics of using EasyEDA. It's relatively straightforward. It should be relatively easy to use. I'll get into some of the features as we use them, but I'm not gonna have a deep, in-depth tutorial on, all the features of EasyEDA. The first thing we need to do is address the USB shell. And I know that the USB shell has 2 ground pins, and then the shell itself also needs to be grounded. So what we can do is we can come over here and we can draw some wires to accomplish that. And we select this little symbol up here is how you draw a wire. All right, so we're just gonna click the button here and we're gonna draw some wires. So we're gonna draw a wire from the ground pin around to here. And you have to kind of click at every vertex. And then we're going to draw a wire from here down to here. And then also draw a wire from here to there, across to here and there. And then we're going to put a ground symbol underneath here. You can see there's a little section here that has the kind of the power signals, and it starts with a VCC, and we just want to select a ground. We don't need the A ground or the P ground. Those have to do with kind of power supply grounding. And we always put ground facing down, and it's nice if you can kind of collect your ground together and wire things to it. We could hang like little grounds off of each one of these, but that would be a little bit messy. The next thing that we need to do is we know that VBus is the 5 volts in that we get, and we need to wire up both of those. Other thing we need to do is we need to wire in these 5.1K resistors on CC1 and CC2, and those need to be wired to ground as well. So we can accomplish that with a nice wire that comes down here and goes to ground. Oops, I think we missed something there. There we go. And you'll notice anytime there's a vertex where there's actually a connection, you get a little dot. If I draw a wire across here to someplace else and there's not a dot, that means that there is no connection there on the schematic. That means it's an independent line. Now, you can't do that on a PCB. It doesn't work because, and again, this is the difference between a schematic and a PCB. A PCB is physical reality. You can't cross 2 wires without them physically connecting. Here we get to pretend a little bit. I guess we just pretend that maybe they go underneath each other and go over each other, something like that. Oh crap, I did that wrong here. And sometimes if you want to move something, if you try and like drag it, you get this like real mess here. So a real top tip here is just to cut. So Control X and then paste it in again, and it will be unfettered by previous connections. So really I wanted that on the CC1 and the C2, and I accidentally put it on S-Bus too. The other thing is that if you know something should not be connected, I know that SBU1 and SBU2 should not be connected. And let's just go ahead and verify that with ChatGPT. Yeah, so it says that I can leave them unconnected. Great. So the DP, so that's P is for positive and N is for negative. So we've got D plus and D minus over here, and those are the ones that connect to this, and they connect to both of them. And the reason that is that if you flip the cable over, one or the other of them will connect. And so that's the beauty of USB-C, is that everything's mirrored around the middle. You see ground, VBus, CC2, SBU, DP2, DN1, and then you have DP1, DN2, CC1, SBU2, VBus, and ground. So you get the same things on either side, and so if you flip it over, you still get the same connections, no matter what. Now I'm going to show you another shortcut that you can do here when you're connecting things up, is that instead of drawing a line, so we could draw a line if we wanted to from DP2, that needs to go over to positive, so that's going to go to the positive, right? And then we could do the negative, and we can draw that over to a negative terminal and connect that to it as well. Okay, that's a little bit messy, you know, whatever. With a simple enough sort of layout, you can do this and it works just fine. But another thing that we can do is that we can use a net label. And so we can name the nets that we're attaching to. And a net is any collection of things that are connected by a contiguous wire. So any set of wires here, so you can see right here, anything connected to ground is on the same net. It's on the ground net. So all of these wires, this resistor, the shell connections, everything, they're all connected to the same net. This wire is all in the same net as well. But you can define a net as well. So we're going to define, well, actually we're going to do two of them here. And then we're just going to call them D plus and D minus. So anything that is connected to a net label of this will be required to have a wire between them. So you're basically saying kind of there's a virtual wire between these two things. When you go to do the PCB, the design rules will require you to draw a wire between everything that's on the same net, but you're just kind of labeling them without having to do wires. And I think that's a really cool feature, although some people don't like schematics that have a heavy use of net labels, where you basically have to go, okay, you know, it's not obvious, you know, what things are connected to what other things. You have to kind of search around and find the labels where they are, but it can really clean up your schematic and make things simpler. So we're going to go ahead and put a DP2. Again, we're going to use the space bar to rotate it. So we're rotating that around, and this is DP2 is going to be D plus because DP is positive. So that's the plus. And then we're going to connect that also down to, and we need to bring this out a little bit here. And connect this down to the other positive right there. Okay. And then you can also just copy these things. So you do Control-C, Control-V, and we can connect the negative, rotate it with the space bar. That's a little bit messy. They have already created symbol libraries for every single component that's out there. And so this is a symbol. So it's a schematic representation of that particular part, right? So it knows all the pins that it has, and it actually kind of knows a little bit of the shape of it. It does, I think, try to preserve kind of the order of the pins around the outside of the package. And so it's cool that they do this for you, but sometimes the physical layout of those pins is really meaningless to a schematic. One of the cheat codes that I found is that you can go ahead and you can edit this guy. And you can then reorder these things. And what I would suggest is that you put things that are going to be connected to ground on the bottom of the chip. You put things that are going to be connected to power or wired to 5 volts or 3 volts at the top of the chip. You kind of group all the data signals together and then group all the things that are going to be not connected together. Now this makes it much easier to wire this guy up. So we can put D plus there, D minus, and we can put our ground down here below. So we just draw a wire across there, right there, wonderful. And maybe let's move this up here, great. And then we can go across here, and we know these are all the not connected ones, so we just put our little not connected symbol on there.
In the dark, where the shadows play, the beat drops heavy like night turns to day. Feel the bass pulse through the crowded space. Lose yourself in the rhythm, find your place. Euphoria's calling, bring the fire. Chase the night, let it take you.
Great, I think we're done. So we can do design and we can check our DRC. Start design rules checking. It found some component pins floating. So it is saying that I left something not connected, and sure enough, I did. That's kind of cool. So it's saying I didn't connect this. So I can mark that as not connected, or I could also just run a wire to it as well. So I don't know, I guess I could just say, you know, that side gets connected that as well. So we're going to do design, check DRC, and it says there were no errors, no warnings. This is really cool. We've wired up every single pin. We've made sure to understand all the connections that we have. We've worked with ChatGPT. We've looked at the datasheet to make sure that we understand the pinout of our CP2102N part and make sure that we really understand how to wire everything up properly. And one thing we can do is we can organize this a little bit better. So if we want to kind of create sections, I don't love the ones where they have the little boxes around everything, but I do love, you know, you can put text on here. So if I want to do ESD, there you go. Okay, so I'm just going to copy and paste that now. So this is going to be USB-C. We're going to call this power. And I think you could tinker with this a lot and kind of restructure things and so forth. It's so simple, but I don't think it matters all that much. But if you're really, really anal about these things, I guarantee you there's all sorts of opinions on the best way to do these and how to block them out and when to put things on different pages and so forth. You can go deeply down that rabbit hole. But the key things that I want to instill in you is to use net labels, not liberally, if you can draw lines between components. So there is a world in which we could have maybe drawn these lines nicely between all these sections and not used many net labels. There are some people that are of the opinion that if you can do that, you should. I think it makes for a messier layout and doesn't really add much clarity with a design that's really this simple. Kind of consolidate your ground connections, so don't hang a lot of little ground labels off of everything that's grounded. Try and just pull them together at the bottom of the chip and have a single ground at the bottom. Try to have your power signals pointing upwards, and at the top of the chip, I think that usually generally makes sense. People like to think in that top-down kind of current flow on a schematic. The other thing is when you're all done, you go into the design menu and you do your check DRC and make sure that you haven't violated any of the rules. There's also this device standardization thing, and I think it will double check and make sure that all the part numbers that you have here are actually valid LCSC or JLCPCB parts. You can see that's all green. So we did our work properly. We don't have any parts that it doesn't know about. One of the things I don't really think comes through in this demo, because you're not using another tool, if you ever try to use another tool, it would become immediately obvious to you the problems that EasyEDA Pro is solving for you very transparently. The cool thing that it's doing is it's maintaining this large searchable parts library, but it's also collating and curating the symbol library. So the list of all the schematic symbols and all the pins and the labels for those pins, somebody has to create those, and they have to create them in a format that's consumable by EasyEDA. And they catalog them and put them in a library. So when you go to place a part and you put it in, you get a symbol. In KiCad, that's not a thing. Like, you can have some kind of standard symbols. So for an 0603 resistor or something like that, there might be a standard symbol for that. But for more complicated, rarer parts like a particular integrated circuit, KiCad just isn't going to have a symbol for it at all. So you'll have to figure out how to import it. You might have to create it yourself. It's a non-trivial task. And again, EasyEDA is taking care of all that for you, and it's integrating it with its own parts library. That's the other cool thing. You saw that we could do the device standardization little check to see and make sure that all the parts that we have in our schematic are actually real JLCPCB parts, and you make sure that you haven't selected anything that they don't have. Now the downside is obviously that you have some lock-in. You can't really use EasyEDA for anything but JLCPCB. I imagine there might be ways you could hack it to do it. Maybe you can extract the Gerbers and send them elsewhere, but it's just made to make it very, very easy to do one-click submission to JLCPCB. So I think this is a really good breaking point. I'm going to produce two videos. The first video is this one, where we are focusing on the design considerations around this project, picking our project, and then the process that we did to pick the parts and then create the schematic that defines the circuit that we're going to make. So at this point, we're absolutely ready to go on to actually laying out our PCB, creating the physical connections in the PCB that we'll use to actually get this project manufactured. Well, thanks again for watching this first video on creating your first PCB. Look for the second video soon. Hopefully it'll be shorter, but maybe not.